In this lecture, we're going to examine hypothesis testing in cases where we have one and two groups of data, or what we just simply refer to as one and two samples. And the way we do this is with something called the t-test. And the t-test is a set of equations, a statistical test based on something called the student's t-distribution that we'll explore in greater detail. And the t-test is used to compare group average against what we will refer to as a test statistic in something called the one sample t-test. So if we only have one group of data, then we can generate a comparison of that group average against a hypothetical or unknown or a population variable. The t-test is also used to calculate the means between, or to compare the averages between two different groups in something we refer to as the independent t-test, or we can compare one group that was measured on two different occasions over two measurements in something referred to as the paired samples t-test. We will also explore differences between the z-test and the t-test. And so the z-test is applied when we know what the population standard deviation is. And that is helpful because there is only one z distribution, that is the normal distribution. However, if we do not know the population standard deviation, then we are required to use the t-test. And this is a little bit more involved because there are many t-distributions, and the t-distribution will depend upon sample size. And so in this illustration here, what we see is a normal distribution with degrees of freedom that approaches infinity in the black curve here. And so this is our normal distribution, but what we see with larger sample sizes, variability will tend to decrease. So t-distribution curves will always be a little bit more platykurtic than the normal distribution because the sample sizes will always be smaller than infinity. And so as the z-test and the normal distribution does not depend upon sample size, the t-distribution does depend on sample size. And so in the red curve here, we see a t-distribution with a small sample size, a small n, and we see a t-distribution in the blue and eventually in the black with a large n. So we see a degrees of freedom of 6 in the blue, and then as the sample size and degrees of freedom continues to increase where it approximates the infinity level, then the t-distribution is no different than the normal distribution. So moving on to using the t-test versus the z-test, the one sample z-test is used if we want to determine if the sample is representative of the population, but the population standard deviation must be known. And so this is the equation that is used to generate a z statistic where we have a sample average, we know what the population average is, and we'll also know what the population standard deviation is, and that will allow us to calculate the standard error of the mean. In the one sample t-test, this is going to take on a very similar format, but we would use the one sample t-test once again to determine if a sample is representative of the population, but we would use this if we do not know what the population standard deviation value is. And as you'll see here, we have a very similar looking equation as we did with the one sample z-test, except that instead of having a z statistic, we calculate a t statistic, but that t statistic has to be specific to a particular degrees of freedom value. We have the same sample average, the same group average. We have the population average, but what you see in the denominator is the sample standard error of the mean. And so in calculating the one sample t-test, we would use the sample standard deviation to generate the sample standard error of the mean, as opposed to the z-test where we would use the known standard deviation of the population. So just as a review, whether we're using a one sample z-test, one sample t-test, or any other type of t-test, we always follow the steps involved with hypothesis testing, which involves us to state the null hypothesis. We then state the alternative. We choose an alpha level. We choose whether it's one or two-tailed, and the one or two-tailed approach will either be directional or non-directional. Directional with the one-tailed approach, non-directional with the two-tailed approach. We state the rejection and the accept rule, as we'll do in this in this series of lectures. We then compute the appropriate statistic. That statistic would be the z-statistic if we were using the z-test, or the t-statistic specific to a degrees of freedom if we were using the t-test. We then make a decision by applying the rejection accept rule from step 4, and then we write the conclusions in context of the study. So our first example is we're going to work a sample here that will involve us using the z-test. And we're going to use the z-test because in this example we have knowledge, we know what the population standard deviation is, and we know what the population average is. And so the question here is, do Ontario University graduates have an average LSAT score that's higher than all Canadian LSAT test takers? So what we see here when we refer to all Canadian LSAT test takers are the population parameters for the entire Canadian population of those LSAT test takers, and we're going to generate a comparison with the results just from Ontario. So we see that the Ontario average, obtained from a sample of 100 students randomly, had an average score of 156, and if we take a look at the population average of 153, we look at this and we might say, well, 156 is greater than 153, so it must be greater. However, with hypothesis testing, we want to make sure that this difference is systematic and not due to random chance. So we begin this process with number 1, where we state the null hypothesis. And so in stating the null hypothesis, it's a null. And so what we state here is that the results from Ontario, the sample is going to be equal to 153, and the sample being representative of the population. Or the alternative, which in which we say that it is not different than 153. So in this particular case, what we see here is a two-tailed or non-directional alternative hypothesis. The directionality is never applied on the null hypothesis, it's always on the alternative hypothesis. So we chose the two-tailed approach. We always make this determination before we examine the data. Because with the two-tailed approach, we're keeping our mind open to the possibility that when the sample data comes in, it could be greater or it could be less than. And because the consequences of making a mistake are not particularly grave, we're selecting a rather conservative alpha level of 0.05. So in setting the rejection accept rule, we always center this back on the null hypothesis. And so in centering it on the null hypothesis, we state that we're going to reject the null hypothesis if the calculated z-statistic, in fact the absolute value of the calculated z-statistic, is at least greater than or equal to the critical z-value. And so the critical z-value at the 0.05 probability level of making that type 1 error and two-tailed is 1.96 on the normal distribution x-axis. Alternatively, we will accept the null hypothesis that the Ontario average is no different than the Canadian average if the z-calculated statistic absolute value is less than the critical z-value of 1.96. And so we start with the equation to calculate the z statistic. And so the first step here is to obtain the population parameter of the standard error of the mean. So we have x bar, which was in the table. We have mu, which was provided, but sigma x bar was not provided. And so this is the first step calculation that we have to perform, in which we take the standard deviation of the population which was provided, and we divide it by the sample size in our study. And so this would be a good time to pause the video and practice this calculation, and then restart the video, and we'll see if you come up with the same value for sigma x bar. Okay, so welcome back, assuming you're restarting the video. So we're going to take our data from the table, we're going to substitute it back into this equation, and so we have 9 divided by the square root of 100. 9 divided by the square root of 100, which is 10, is 0.9, and that's our value for the standard error of the mean. We then take this value and we substitute it into the z equation, and by substituting it into the z equation from the data obtained from the table, we have the sample average of 156, the population average of 153. We go through our calculations and we find a z-value of 3.33, which is going to sit pretty far out on the x-axis of the normal distribution, and we'll see an illustration of that on the next slide. So moving on to the next step, we find that the absolute value of z is 3.33, which exceeds the critical value of 1.96. Therefore, since the calculated z exceeds the critical value, we therefore reject the null hypothesis. And recall, the null hypothesis stated that the sample would be equal to the would be representative of the population and be equal to 153. So in rejecting it, we accept the alternative hypothesis in that it is not equal to 153. And so we see on this illustration of a normal distribution, here we see our value of 3.33 way out on the right hand side, which far exceeds our critical value. And so we have two critical values here because we chose the two-tailed approach. And so if we are within the critical values, then we're within 95% of the entire population. However, with 2.5% on the negative side, 2.5% on the positive side, what we clearly see here is that our test statistic, our calculated statistic of 3.33 sits way out on the tail here, well into the 2.5% range, and so we would conclude that Ontario graduates score significantly, and so we only use the term significantly when we reject the null hypothesis with a probability of less than 0.05, or a probability that's less than 5% of committing a type 1 error. The possibility is still there, but it's very, very low. So Ontario graduates score significantly higher on the LSAT than all Canadian LSAT takers. So in restating this, if we obtained a different another random sample of Ontario graduate LSAT test takers. Remember, we obtained a sample of 100 test takers. If we obtained a different sample, a different random sample of 100 test takers, we would have a 95% chance that their results would score greater than the Canadian average as well. So this ends the first part of our lecture on the 1 and 2 sample case.